Calculus 2 is about the most fun math class that I think I ever teach. Just enjoy every little thing about it, including all my typos. But we'll start with, actually, before I even begin to talk about our first lesson, which is how to find the area between curves. That would be like this purple area here. How do you find the area between curves? Well, there's a mnemonic device to learn, and it's SAALI, and it stands for subdivide the interval, approximate a part of the region, or approximate some particular thing you're trying to find, only a small portion of the thing you're trying to find, then add all the approximations, take that to the limit, and then identify the integral from the Riemann sum that you come up with when you take it to the limit. So, area between curves we can subdivide. We'll take this area between the curves and chop it up into small rectangles. That's the subdividing part. Only they're not really rectangles because they're not like these two sides aren't parallel, and they're not at right angles with the parts. But that's where the approximation part comes in. We're going to approximate that piece, one of those pieces, with a rectangle whose height is f of c sub k minus g of c sub k, where c sub k is some x in the interval delta x sub k, and delta x sub k is the width of the rectangle. So even though it's true that this piece isn't a rectangle exactly, we're going to approximate it with this rectangle. And of course, the area of this rectangle is delta x sub k times f of ck minus g of ck. What does that give us? Well, when we add them all up, then the area between the curves will approximately be equal to all of those rectangles that we've subdivided. Actually, we subdivided technically the interval a, b. If this was a here and this was b here, we've subdivided that entire interval by the fancy word is partitioning the interval into a bunch of subintervals. But each subinterval is a width delta x sub k. But the idea is we chop that up into subintervals, add up all the rectangles we make from the subintervals, and that would be approximately equal to the area between the curves. However, it would be exactly equal, that's why this type of equal sign here instead of this type, exactly equal to the limit as the largest of those subintervals, the width of the largest of those subintervals approaches 0. And if we make that happen, then the area between curves will be exactly that. And if we look carefully at this particular expression, you should see, oh golly, that's just a Riemannian sum. And when the limit of maximum delta x approaches 0 for a Riemannian sum like that, then you should see that that is the integral from a to b of f of x minus g of x dx. And the problem is now reduced to finding this definite integral. Now, that's the SAALI way of looking at this one. Can I discuss freely? I hope you don't mind if I discuss freely with you another way of looking at this particular problem. Another way of looking at this particular problem would be to say it's the area under the blue graph from a to b, which you already know how to use an integral to find that, then minus the area under the green graph. So if we take the area under the blue graph between the x-axis and the blue graph and subtract the area under the green graph, we would get exactly the area of this shaded region that we've been seeking all along. So that is another way of looking at this particular problem, but please get to know this acronym and what it stands for, because other problems that aren't quite so simple as finding the area between curves are going to require this methodology to come up with formulas, etc., that we're going to need to find interesting areas. And actually, once you know this particular technique, there are many problems that can be solved with integration.